Okay, for this one we have another example of using rate laws, and they give us the reaction here. This looks like it could be the production of ammonia. The rate law for this reaction is equal to rate is equal to K times concentration of our first reactant. It's in the first power because the exponent there is a 1, and hydrogen is in the second power. Overall reaction order will be the sum of those individual reaction orders, so it's third order overall. I do want to point out, notice that this is again a third order reaction, just like the previous example. So that tells me right off the bat what the units of K are going to be. The units of K are going to be the exact same that they were in the previous example, because the units for your rate constant will vary depending on the overall order of the reaction. So these are the units for K when the overall order of the reaction is third order. Okay. So the next one, they say at a certain concentration of N2 and H2, the initial rate is 8 times 10 to the 5, a very large number. They say, what would the initial rate of the reaction be if the concentration of N2 were doubled? So it's telling me that this reaction takes place very, very quickly. The initial rate is a really, really, really big number. Okay. Well, let's say, what will the initial rate be if I double N2? Well, let's look. Nitrogen is in the first order for this reaction, meaning if I double the concentration of N2, then the reaction rate also doubles by the same factor. So if I double it, it doubles. If I triple it, it triples. If I quadruple it, it quadruples. So they say double it. So what will happen to the rate? Rate will also double. So this should be, we'll take 8.0 times 10 to the 5. And if I multiply this times 2, what I should get is 1.6 times 10 to the 6. And my units are mOS. Okay. Then they say the rate of the reaction is measured to be. So we have an initial rate and we have initial concentrations, or this could be at a particular moment. The rate is this when the concentration of N2 is this and the concentration of H2 is that. They want us to find the rate constant. Okay. Now again, the rate constant, as a constant, it's going to be the same for this reaction regardless of what, how early or how late in the reaction it is, as long as the temperature stays the same. So if we find K once, K for this reaction will always be the same as long as the temperature doesn't change. So how do we find K? Well, of course, we set up our rate law. Rate is equal to K times N2 times H2, which is in the second order. We're going to solve for K. Okay, so K is equal to rate divided by the concentration of N2 times the concentration of H2 to the second power. The rate is 0.6. Our units. The concentration of N2 is 1.5 and H2 is 0.48. So 1.5 molar, 0.48 molar. But this is squared. K is equal to 0.6 divided by 1.5 molar times, and 0.48 squared is 0.2304. And I'm not going to round too early. Try to get out of the habit of rounding intermediate values. Also have to square my unit. So this becomes that squared. K is equal to 0.6 divided by this times this, which comes out to be 0.3456. If I multiply m squared by m, it's m to the third power. So K is equal to 0.6 divided by that, 1.7 1.736. The units will be m to the minus 2 seconds to the minus 1. So 1.736 per m squared times seconds. And that's how you would say, verbalize these units of response. They wanted the 2 significant digits, I believe. So our final answer, submitted answer in ALEKS, would be 1.7 m to the minus 2 times seconds to the minus 1. Notice again that K is fairly large. It's pretty big, unlike the last example. But this reaction proceeds very, very quickly. Okay? So we place this 1.7.